So last time we had explored this second or other orthogonality relations, which say what you see here. I mean, essentially, we have interpreted the orthogonality relations as saying that a certain matrix is the inverse of another matrix. Say A times B equals the identity, square matrices. And of course, if A times B is the identity, then B times A is the identity. And this is what happens if you look at the matrix that way. Because if you do the multiplication A times B, then you're summing over the element of G, which are which index the columns of the first matrix and the rows of the second matrix. If you do B times A, you sum, as you see here, over the irreducible characters which label the rows of the first matrix and the column of the second one. So when you exchange, you sum over those. And we found that if you do this sum, which is essentially the scalar product, the inner product, keep in mind this relation here, then we obtain the centralizer of Z when Z and W are conjugate. And if they are conjugate, the centralizer of Z and the centralizer of W are conjugate. So the order is the same, and zero otherwise. And as a consequence, if in particular we take not only Z and W to be conjugate, but to be equal, then we find that the order of the centralizer of an element Z of G is, well, here we found the square of the absolute value is the sum over the irreducible characters of the square of the absolute value of the character computed on Z. Here you see one of the, well, one might call it fascinating things of characters, that when you define the centralizer of an element in a group, linear representation don't enter in definition. They have nothing to do with it. But then we found that we can express the centralizer in terms of this irreducible representation, actually, of their characters. And as a consequence, we found a quick proof of this fact that if you have a finite group and then a normal subgroup and then the quotient group, okay, let me minimize this, the quotient group, then when going from the group G to the quotient group G over N, the order of the centralizer does not increase, okay? Does not increase. And here there's a quick proof using characters and using this formula, okay? The idea being that, that every representation and then every character of the quotient can be lifted to a character representation of the whole G. And so when you do this sum over the reducible character of G over N, this is part of the same sum for the reducible character of G. And hence you have this inequality. And I promised last time to have a purely group theoretic proof of this inequality, which isn't difficult at all, but in a sense, having these tools, this identity on characters, sometimes it makes it easier to discover formulas that then can be proved also in a character-free fashion. So let's see what's this other proof. The proof goes like this. So remember, what's the situation? No, so character-free proof. So in a sense, an elementary proof, which does not require all the theory we've seen so far, a proof that could have been given already in the Teoria dei Gruppi course in the third year, because it just involves groups element. So what's the order of the centralizer of in G of an element X? Okay, so G a finite group and a normal subgroup of G, and X an element of G. Well, by orbit stabilizer, this equals the order of G divided by the orbit, and this is the conjugacy class, okay? This is the order of the conjugacy class. So xg is the set of conjugate, okay? Where we write this as x to the g to simplify things, okay? And that's one of the two terms here, okay? This is the leftmost term, and then we have the other term, which we will treat accordingly. So now we are in the quotient group. So I mean, the proof is elementary, but it's important to point out which is which. So this is a coset, okay, which is an element, so a single element of G over n. Then you can also see this as a subset of G, and then it will have the order of n elements, okay? Because all cosets have the same element. But this coset is a single element of the quotient group G over n. Then you can apply orbit stabilizer once again, and this time the group is G over n. And here you have the conjugacy class of xn in G over n. So you write this at x to the n, G over n, okay? Of course, Lagrange tells you that the order of G, of the quotient group G over n is exactly the order of G over n. So you can, so Lagrange, so you find, so the order of this order of G over n, so I took it to the denominator here, okay? So this is the first term, this is the second term. Our goal is to prove, let's write it in red. Okay, so we are going to give a character-free proof, so we forget about the proof we had with characters, and then we need to prove that this is greater than or equal to this. Of course, since the denominator of the numerator of these two fractions is the same, our goal is to prove that the denominator of the first one is less than or equal than the denominator of the second one, to be proved. And this, I think I will copy then, that the order of x to the g is less than or equal to the order of n times. Okay, so this to be proved. We're going to prove that the denominator of the first fraction is less than or equal to the denominator of the second fraction. Since the numerator is the same, this will mean that the first fraction is greater than or equal to the second. Let's copy this to the next. Yes. No, this is not done well. Let me do it again. Better. Add to next page. Great. So this is what we have to prove. So we look at this term, okay? At this term. What's this? So this is the conjugacy class. No, sorry. This is the conjugacy class of the element xn of G over n in the group G over n. Okay, so according to the definition that we already reviewed for the conjugacy class in G of x, this will be the set of all conjugates, okay, Sg of this form, Sg runs through G. Okay, I could have written Gn in G over n, but then all yes, but then it's the same to see to write G in G, because I mean when Gn writes yeah varies in G over n, ranges in G over n, you get the same. So these are conjugates in G over n. So these are this is a conjugate, so inverse element xn, well, let's put parentheses for clarity, and then gn, again g in g. And this, well, how do you operate with cosets? Well, the inverse of the coset is the coset of the inverse. And then when you do a product of coset, you simply cosets, you simply take the product of the elements here. Let's put parentheses here for clarity. And of course, you see that this is just x to the g, the conjugate in g, n. Okay, so this is this object here. But this is important. This is so far a subset of G over n. Okay, so each element this is one single element of G over n. But then these single elements of G over n are cosets. So they are subsets of G, okay? Okay, it's a set of all products. And so we may consider their union. The union of all these. Which is a subset of G, okay? Because this object, this time, we see it as a subset of G, okay? And then we can consider this union. And how many elements does this union have? Well, how many elements? Well, this is a union of cosets, okay? You know that the cosets form a partition, okay? So because they are the classes of a certain equivalent relations, since cosets of n form a partition of G. To count how many elements you have in this union, you simply say, count the number of elements, the number of these cosets, and multiply by the order of the cosets. So the order of this, the size of this, is order of n, which is equals the order of each coset, because we know by Lagrange. I mean, it's in the proof of Lagrange's theorem that all cosets have the same number of elements time number of cosets, of distinct cosets, say. But this we know already because it's the number of elements in this conjugacy class, okay? Because we have taken the union of all cosets which form the conjugacy class, okay? So this equals the order of the conjugacy class, okay? So once more, you look at this conjugacy class, okay? This conjugacy class is a subset of G over n, and there's the number of elements which equals by, well, this, okay, simply the size of this conjugacy class. If you look at it, at this conjugacy class as a subset of G, you can take the union, and then the number of elements here will be the number of elements of n times this, okay? So let's go to the next page, and then we can see that the union of this will have number of elements when times the size of this conjugacy class. Okay? But note that this union, okay? Yeah, I'll copy it. So it's a union of all these subsets, but in the subset, in this coset for G in G, there will be x to the G. So this contains x to the G, G in G. You simply note that that if you in each coset you take n the element here equals to 1, you get x to the G. Okay, and so you see that the number of elements of this coset of this union is greater than or equal, and that's just x to the G, which is exactly what we wanted to prove. Okay, because this equals this, and we have proved that this is greater than or equal than this. Okay, it's the two denominators of the fractions that I'll show you again, and I'll come back to this page. Okay, I've shown that this is greater than or equal than this. So what I have to prove here, okay? It's not a difficult proof, but it's tricky because you have to be clear when you are considering a coset as an element of G over n or a subset of G, okay? Because as an element of G over n, it's a single element. And here we are counting how many of these cosets we have. If you look at it as subset of G, then the number of elements in this coset has to be multiplied by the order of n. So we have proved this. Let's consider an example. It's a very simple example. G will be S3, and N will be A3. That will be the subgroup generated by 1, 2, 3. And we want simply to compare two conjugacy classes two centralizers in G and G over N. And we will see that in one case, the centralizer preserves the order, and in the other, the order decreases. Because remember that we have proved we have proved that the order of centralizer does not increase. So it can stay equal or it can decrease when going to the quotient group. And so the first part of the example is, say, 1, take G equals 1, 2, okay? And then we know very well that let me change notation to have the same notation we are using here. So let's take X to be the 2 cycle 1, 2, okay? And then we know that X to the G is, I mean, conjugacy in a symmetric group is very simple. It is given by the free 2 cycles, and so X to the G order 3. Okay, well, okay. What's the centralizer in G of X? Well, this is very simple because, of course, it contains 1 and 1, 2. This is B in X, okay? It cannot be bigger because this already has 2 elements, and it's a subgroup, and the centralizer subgroup, and by Lagrange, the only subgroup properly containing 1, 1, 2, that is the subgroup generated by 1, 2, is the whole S3. But we know that these do not commute. Okay, so 1, 2, 3 is not in the centralizer. So this is a centralizer of order 2. Okay. What's the centralizer? What's the centralizer in G over N of Xn? Well, G over n, of course, let's write it here. G over n is order 2, so it's an abelian group. So we simply know that the order of the centralizer will be 2 because this is abelian. So the centralizer of anything will have order 2. So we see that the order has remained the same. Okay, but if the order has remained the same, this means that the two denominators will have will have been the same. And so what are the two denominators? Let's look at so we have x to the g. Remember, x is just 1, 2 here. And what we have proved previously is that this is contained in xgn. Yes, because I should have noticed this before. This union, okay, let me write it in red here. Okay, no, I'll write it in the, because this object is nothing else that, yeah, okay, that the union of the xgn, g in g, okay, because this union consists of all elements in which the first term is a conjugate of x and the second element is an element of n. So it's the conjugacy class of x times n, okay? Once more, look at this union. An element of the union can be written as a conjugate of x, okay? So an element here times an element of n, okay? So if the centralizer has not changed, this means that in this case, thus, in this case, the two sets must be the same. Because the order of the two sets are the order of the order of the two denominators of those fractions. But why are these sets the same? Because you see, here you have just a conjugate of x. Here you have the conjugate of x multiplied by element of n. But the reason why this works is very simple, because an element, so we have an element of x to the g and an element of n, okay? An element here is just a two cycle, okay? ij, because as we recalled, the conjugate or the conjugacy class of 1, 2 is just the set of the 3 two cycles, okay? And n, remember, n is a3, so it's generated by 1, 2, 3. So the element here is a power of 1, 2, 3. Let's use k, okay? But you see the product of these two, this is an odd permutation, this is even, okay? And so the product will be odd. But what are the odd permutations in S3? Well, it would be another two cycle, okay? Which is a conjugate of x. So we don't need to know exactly what goes on. We simply know that odd times even is odd, and the three odd elements in S3 are the two cycles. And so we have seen that this equals x to the g. When you multiply a conjugate of g of x by an element of n, you still get a conjugate of x, okay? So the two sets are the same. Remember that I've taken this opportunity to rewrite this in this form, okay? And thus, this is the reason why the centralizer stayed the same. Let's look at a different case. This time we take x equals 1, 2, 3. This time the centralizers change. The reason being that, for the same reason that, so remember G is S3 here, okay? And N is 1, 2, 3 is A3. But because the centralizer in G of x, x has become 1, 2, 3 now. Okay, it used to be 1, 2, now it's 1, 2, 3. This has order 3. I mean, the centralizer in G of 1, 2, 3, for the same reason that we saw with the cycle 1, 2, is the cyclic subgroup generated by 1, 2, 3. But when you look at the centralizer in G over n of xn, well, as we noted, G over n is a group of order 2, so it's cyclic, abelian group. So the centralizer of anything is 2. So you see, here we have an example where this centralizer, the order of the centralizer has decreased going to the quotient. So this means that these two sets in this case won't be equal. Why is it so? Well, let's look at this. So so remember this time x is 1, 2, 3. So what's x to the g? Well, again, it's easy to do the conjugation in symmetric groups. It's simply the set of the two three cycles, okay? So what happens when you consider x to the g n? So the two are if the two are equal, then the centralizer are equal. Since the centralizer are not the same, it means that this will be bigger. And why is it bigger? Well, it's rather easy because you multiply all elements of this, okay, times n. What's n? N is the group generated by 1, 2, 3, okay? And so here you have what? The group generated by 1, 2, 3. So 1, 1, 2, 3, and 1, 3, 2. And now you see what happens. That so this is the product of the subset, which is the set of all products. In this, you have in particular the product of 1, 2, 3. Okay, no, in red, it's better in red. Let's say 1, 2, 3 times 1, 3, 2. Okay, so this contains 1. Okay, and of course, 1 is not here. So in this case, you see that x to the g is strictly smaller, okay, than x to the gn. And that's the reason why the centralizer has decreased, okay? So in the first case, when x was the 2 cycle 1, 2, you multiply a conjugate of 1, 2 by an element of n, and you still get a conjugate. So these two sets are equal. This time, this is not the case because in this product, you have more elements. So you have a larger denominator, and this is the reason why the two centralizers are different, okay? So we have seen this in practice. Good. The example of S3 will be useful for what follows next. It was okay. So let's okay. So what I want to do now, it gives you a formula for something that we have already touched upon. There is the product of two elements in the center of the group algebra. But let's first consider this factor. Products, no, in black. Products of conjugacy classes. Okay, so let G be a finite group. This does not come as a surprise, I suppose. And let C, D be two conjugacy classes of elements. Of G, okay? Then it's a fact that in practice we have already seen. Then consider CD, the product, which is the set, as usual, of products. No, sorry, this is C. So the set of products. And the point is, this is a union of conjugacy classes. Why? Well, what I want to prove that if an element is in C times D, then all of its conjugates are in there. So if CD, with the usual notation, is in capital C, capital D, then what happens to its? Then I claim it's an easy claim. It's not the most difficult claim I will be making in this course. Then I claim that CD to the G is in CD for all G in G, which means it's a union of conjugacy classes. I mean, if there is an element that there's all conjugacy class. But the reason is very simple, because this is C to the G, this is D to the G, and since C and D are two conjugacy classes, this is in C and this is in D, okay? And so this is in CD. because C and D are conjugacy classes. So when you conjugate an element of C, you obtain again an element of C. Okay, so it's a union of conjugacy classes. Let's consider an extremely simple example related to what we have just seen. So we consider example. Consider G being S3, and the two conjugacy classes will be the conjugacy class of 1, 2. Okay, and D will be the conjugacy class of 1, 2, 3. Okay, and we want to know what's the product CD. Okay, it's a union of conjugacy classes, and so we'll do it in this order. So we build the table. What makes this not particularly difficult to compute is that we know already that since this is odd and this is even, okay, these elements are odd and these are even, all these elements inside here are writing in red and I'll delete it, will be odd, okay? So there will be elements, there will be 2 cycles, okay? Because they even times odd. And then there's not much to compute here because, for instance, consider this product. 1 goes in 2, 2 goes in 3. Okay, so this has to be 1, 3. Okay, because I mean, if you know that it has to be a 2 cycle, and 1 goes to 3, then it has to be 1, 3. So 1 goes to 2, 2 goes to 1. So 1 is fixed, so it must be 2, 3. Okay. 1 goes to 3, 3 goes to 1. Okay, this must be another instance of 2, 3. 1 goes to 3, 3 goes to 2. That has to be 1, 2. 2 goes to 3, 3 goes to 1. And so this has to be 1, 2. Okay. 2 goes to 3, 3 goes to 2. This is fixed, so this will be 1, 3. Okay. So what we have found that CD, well, of course we knew already. It's let's say it's C. Okay. We knew it there to be odd, but note that you obtain twice this coset. Okay, so this is one copy of the coset, and this is another copy of the coset. So when you just look at the sets, which of course C times D is simply C. Okay, but we would like to keep track also of the multiplicity, okay? Because each element of C appears twice. Of course, if you look at just set-wise, you don't see. I mean, in a set, each element counts exactly 1. Okay, so how can you keep track of this multiplicity? Well, the trick is the following. To look at, so to keep track of the multiplicity. This is in blue, but why not? Work in the center of the group algebra. Okay, because I mean, we have seen this several times. The center of the group algebra has a basis. Of course, it has many bases. It has a basis at a vector space, which is given by the sums over the conjugacy classes. So 2 particular elements in the center. So the center of the group algebra is written like this. Okay, center of the group algebra. So 2 elements of the center will be what I write as sum of C, which is the sum of the 3 elements, where the order, of course, it doesn't matter. And the sum over D will be 1, 2, 3 plus 1, 3, 2. So when you do this, so these are 2 elements in the center of the group algebra, okay? Let's call it Z for simplicity, because I don't have any space to write the whole thing here. So what happens when you multiply this? So remember that, yes, I constructed the group algebra with a convolution product and the like. But really what happens, you have this sum, you have this sum, you distribute. I mean, it's a ring, it's an algebra, so it's a ring. You distribute and then collect, okay? So there are 3 elements here, there are 2 elements here, so it will be 6 elements here, okay? So this is 3 elements, this is 2, the products will be 6 elements. And what will this 6 element be? Exactly this 6 element here. So what we obtain here, of course we obtain C, but you obtain it twice, okay? So this is twice sum of C, okay? Because I mean, if you just write sum over C, it's just 3 elements. So you obtain it twice. So this element here, by working in the center of the group algebra, you can keep track of how many times an element occurs when you consider the product. So just taking the product of 2 conjugacy classes, which is something, say, character-free in a sense, it just give you the elements that appear. If you do it in the group algebra, you also keep track of the fact that we have seen these elements appear twice. And now the point is, we want to obtain a formula for these numbers here. So because the product of 2 conjugacy class is a union, classes is a union of conjugacy classes, when you do the product of 2 things like this, you will obtain a linear combination with positive or, say, non-negative coefficient, integer coefficients. We discussed this already a few lessons earlier of the sums of conjugacy classes. We want to determine these coefficients here. So I think I will state the result, because then the proof is not long, but it's a bit involved, and I'll leave it for tomorrow. And so the theorem is the following. It's a theorem of Burnside. And before I state the theorem of Burnside, once again, what we were doing in the top part of this board was to know that, well, the product of 2 conjugacy classes in a group is a union of conjugacy classes, and I want to keep track of how many times a conjugacy class appears. Okay, for instance, here C appears twice. So this question is a purely group theoretical question. Okay, C times D is a union of conjugacy classes, so this would be C, but since I have 6 products, it appears twice. How can I know how many times a conjugacy classes appears? So the idea is to compute this coefficient. And to compute this coefficient, you need characters, okay? So this is an important pattern. A purely group theoretical question, how many times do I get this C when I multiply C times D? We'll have, as you'll see, we'll have a character theoretic solution. The rather involved formula is, but the proof then is shorted. In a sense, the proof is shorter than the statement. So let G be a finite group. And let CD, CD be 2 conjugacy classes. In G. Then we claim that if you do the product of the sums, exactly as before, this is the sum over E. We'll see what's this. So this will be a sum of conjugacy classes. So this runs over all conjugacy classes. With certain coefficients, which depends on C, D, and E. And we have already seen earlier, but I'll recall this tomorrow, that these are non-negative integers, okay? And the theorem of Bernstein tells you a formula for this, okay? And the formula will be the following. If C is the class of X, D is the class of Y, and E is the class of Z to the G, then lambda CDE is, well, there is a fraction in front, which is the order of G divided by the centralizer of X, order of centralizer of X times the order of centralizer of Y. And then here you have a sum over the reducible characters of a rather strange object. You have chi of 1, the degree of the character, and then chi of X, chi of Y, chi of Z inverse. Okay. It looks ugly, but when we'll see that in practice we will just be using the second or the other orthogonality relations. Okay, so once more, I recall this tomorrow. These are two elements of the center of the group algebra. Okay, so when you take this product, it will be again in the center. So it will be a linear combination of the oh, sorry, misprint. Okay, it will be a linear combination of sums of conjugacy classes, because these sums of the conjugacy classes are a basis of the center as a vector space. And we had already seen, but I recall tomorrow, that these are non-negative integers. Okay, it could be zero, they could be zero, but how do you determine this? And this is the formula. So you have a purely group theoretic thing, and then you have this formula, which is a sum of the irreducible characters. And the fact that you are summing of the irreducible characters, and you will see tomorrow, comes precisely from the other orthogonality relations which involve exactly sums of this type. And then once we have proved this formula, we'll see again, although it's a rather complicated way of doing business here, we'll see where these two come from, okay? Comes from. That is, we recompute this by using the formula, although, I mean, it's a rather involved way of doing things here. So I think that's all for today. So I'll start tomorrow's lecture by proving this, by recalling these facts, and then by proving Burnside theorem. That's all for today. Thank you very much for your attention.